This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss question bank on long answer questions on Module 5 Nanotechnology. So the first 10 theory questions I have covered in the earlier presentation. So the 11th one is explain the precipitation and combustion methods of fabricating nanomaterials. So we need to explain what is precipitation and what is combustion method. And these two methods are used to fabricate nanomaterials. So we have to discuss these two methods. Precipitation method. So the principle of this technique is to getting the precipitation of our desired materials after reactions occurred by mixing solutes and solvents. So the technique of this precipitation is that precipitation of our desired materials after reactions occurred by mixing solutes and solvents. So we are going to take solute and we are going to take solvent. We are going to mix these solute and solvent. After reactions of these two solute and solvent, we are going to get the desired material in this precipitation method. So that is the technique. So in this case, the precipitation of ions may occur slowly. By washing with suitable reagents or drying up the precipitation, one can get the required nanomaterials. So once we mix the solute and solvent, we are going to get, after reactions, we are going to get a material, and that by drying up this precipitation material, we are going to get the required nanomaterials. So this precipitation method is widely used to synthesize metal oxides and insulators with broad band gap along with a suitable surface. So in this precipitation process, the desired component is precipitated from the solution. Precipitation is the formation of a solid in a solution. So there will be a solid formation in the solution, and then solid formed is called precipitation. So whatever solid we are going to get, that is called as precipitate. So a precipitation reaction occurs when water solutions of two different ionic compounds are mixed and an insoluble solid separates out of the solution. So how do we get this precipitation? This precipitate we get when water solutions of two different ionic compounds. When two ionic compounds in water are mixed and insoluble solid. So when we mix these two compounds, then there is a formation of solid that separates out from the solution. So that is how we get the precipitate. So this is the precipitation technique, and this is the schematic of the precipitation method. Okay, so first we take solute and solvent. When we mix these two, we are going to get this precipitate. So there is a formation of solid that separates out from the solution. Okay, so this is the schematic of this precipitation method. Next one is combustion method. So this technique is widely used to obtain metal oxide and insulator nanomaterials as in precipitation method. In this technique, first one should make a solution with solutes and solvents. Again, we need to make a solution with both solutes and solvent. Sometimes making solution may require stirring provision. So to make solution, we may need to use stirring to get the required solution. Then the solution is heated, and once the solution reached auto ignition temperature, it will start to burn by indication of flames with evaporation of some gases. So once we get this solution, we are going to heat the solution. By heating the solution, once the solution reaches auto ignition temperature. When we heat the solution, when the temperature of the solution reaches the auto ignition temperature, then we will see the flames. So the solution will burn, and by the indication of flames with evaporation of some unwanted gases. When the unwanted gases are evaporated, then we are going to get the required nanomaterials. So this is the schematic of this combustion method. You can see the burning, or once we heat this solution, there will be auto ignition temperature and there will be flames in the solution, and then we are going to get this kind of nanomaterial in this combustion method. Why surface area to volume ratio is very large for nanoparticles compared to bulk materials? Explained with an example. So we need to explain why surface area to volume ratio is large for nanomaterials. Okay, so we have defined, we have discussed that these factors, surface area to volume ratio and quantum confinement effect, these are the two important factors that affect the properties of nanomaterials. So in this, we are going to discuss about surface area to volume ratio, and this is large for nanomaterials. So we need to discuss why surface area to volume ratio is large for nanomaterials with an example. Okay, so here I have taken a cube. Okay, so for a cube, we know that the surface area of a cube is 6a square, because each face of the cube is a square, and area of a square is a square, right? And there are 6 such squares, so the surface area of a cube is 6a square, and volume is a cube, because each side is of length a. Okay, so the surface area to volume ratio is 6 by a for a cube. Okay. So as I decrease the size of this cube, so what I have done, first I have taken 1 meter cube. The length of each side of this cube is 1 meter. So then what I have done, so the surface area I got is 6 meters square. Now I am going to divide this cube into 4 parts. So basically there are totally 8 divisions. So each one is of half meter now. So this is half meter, this is half meter, in this side also half meter, half meter. So there is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 such small cubes, and each length of the cube is now half meter. Okay, so then I am going to get area as 12 meters square. And when I divide further, 1 by 4 meter length, each side of the cube is 1 by 4, then I am going to get 18 meters square. When I divide further and further, I am going to increase the surface area to volume ratio. Okay, so by taking the cube as an example, we discussed that the surface area to volume ratio increases as you reduce the size of the particle from bulk to nano. So this is bulk, where each side of the cube is 1 meter, but now I have divided this into very small cubes of 0.1 nanometers. Okay, so then I have gone from bulk to nano, and then I found that the surface area to volume ratio has become 2.5 acres. Okay, so 6 meters squares to 2.5 acres. So it's very large. So when you go from bulk size to nano size, the surface area to volume ratio will increase. Okay, so that is what we have proved here by taking the example of cube. Okay, so when the surface area to volume ratio increases, then the materials which are not catalytic will become catalytic, which are inert will become reactive, and so on and so forth. Okay, so then the next question is, explain nanoscience and nanotechnology. So we need to discuss what is nanoscience and what is nanotechnology. Nanoscience is a basic of nanotechnology. So whatever we are discussing about nanotechnology, all the nanotechnology depends on nanoscience, and nanoscience relies on quantum theory. So nanoscience basically explains the nanotechnology, and the rules are based on quantum theory. So nanoscience basically takes the laws from quantum theory to explain nanotechnology. So we have defined here nanoscience. Nanoscience can be defined as the study of phenomenon and manipulation of materials at atomic, molecular and macromolecular scales, where properties differ significantly from the larger size. So nanoscience is defined as a phenomenon in which the materials change their properties when the size goes from bulk to nano size. Okay, so many diagnostic equipments are manufactured. For example, transmission electron microscope, scanning tunneling microscope, and atomic force microscope, MRI, which we use in medical field, have been invented using this nanotechnology. And we can explain this nanotechnology using nanoscience that is based on quantum theory. Nanotechnology is the day-to-day developing subject with large number of applications. So nanotechnology has a wide variety of applications in different fields. Nanotechnology has the potential to create many new materials and devices with wide-ranging applications such as in medicine, electronics, and production. So using nanotechnology, we can develop many materials, new materials, and new devices which can be used in medicine, electronics, and energy production. So nanotechnology is the design and development of techniques, instruments, and devices for fabrication, characterization, and application of nanoparticles. So what is nanotechnology? Nanotechnology is nothing but the development and design of techniques, new instruments and new devices, and which can be used to not only to characterize a material, but they can also used in medicine and electronic industry and energy production. So that is what is nanotechnology. And how did this nanotechnology start? Where did it start? The word nanotechnology is not relatively new, but it has been there for a long time. In fourth century, Roman glassmakers fabricated glasses containing nano-sized materials. Similarly, gold nanoparticles are made long ago. So this nanotechnology has been there for a long time. So it has actually started in 4th century, where these Roman glass makers fabricated glasses, and we already know that gold nanoparticles are made long ago, and so it has started from long time. But the word nanotechnology is given recently. So the concept of nanotechnology was first given by Richard Feynman. So he is the first scientist who gave the name of nanotechnology, Richard Feynman. And in 18th century, British scientists Thomas Wedgwood and Sir Humphrey Davy were able to provide images using their experiments. So the Richard Feynman was the first person to give the name nanotechnology, but there are other scientists who supported him by doing experiments. In 1960, Richard Feynman presented a visionary and prophetic lecture at a meeting of American Physical Society entitled "There is plenty of room at the bottom." Okay, so we can do so many experiments and develop or fabricate new devices, materials that can be used in different fields. So that is what is the meaning of "there is plenty of room at the bottom." So this is the title of the lecture given by Richard Feynman in American Physical Society in 1960, where he speculated on the possibility and potential of nano-sized materials. So yeah, so the term nanotechnology was defined by Tokyo Science University professor Tony Gucci in 1974 as follows. Nanotechnology mainly consists of the processing of separation, consolidation and deformation of materials by one atom or by one molecule. Okay, so that is how this professor defined the term nanotechnology. So we have basically discussed what is nanoscience and nanotechnology in detail. The 14th question is, explain sol gel synthesis for producing nanomaterials. Explain with the help of a neat sketch. So we need to explain what is sol gel process with a neat diagram. Sol gel method involves the formation of a colloidal suspension and gelation of the solution to form nanopowders in a continuous liquid phase gel. Okay. So first, in sol gel method, first we are going to prepare a solution, sol gel, solution and gelation. First we are going to prepare a solution and we are going to wait for some time so that the solution get gelated. That means the solution will make polymer networks to form gel, and then from this gel we are going to get different nanoparticles by supercritical drying and drying. Okay, so what is a colloid? Colloid is a mixture in which one of an insoluble substance of particles are suspended throughout another substance. Okay, so that is what is colloid. So what do we do in this sol gel method? Initially, a homogeneous solution of a material is prepared. First, we are going to prepare a homogeneous solution and that is used for nano fabrication. So the solution is deposited on a suitable substrate. We are going to deposit the solution on a substrate. You can deposit the solution on a substrate by spraying, dipping or spinning. So there are various methods by which you can deposit the solution on a substrate. It is kept for a while for gelation. So we are going to wait for some time so that the solution is going to get gelated or to form polymer networks. So during this gelation time, the material gradually loses. What happens during this gelation time? The material gradually loses its fluidity and it undergoes a transition from viscous liquid to elastic solid state. So the liquid will become like a solid. Okay, so this time depends on viscosity and temperature of the solution. So once we get this solid elastic solid state, we can get different types of materials. For example, once we have the solution, this colloidal solution, you can directly take this colloidal solution and dry it to get powder, nano powder, or you can take this colloidal solution and spin or dip on a substrate to get dense thin film. You can get thin films, or you can draw this solution to get fibers, and you can get this or you can wait for some gelation time where you get this solution becomes gel, and this you can dry this gel to get powders again, or you can supercritical drying this gel, you get dense ceramic materials. Okay, so there are, you can get different types of materials using this sol gel method. For example, you can get thin film, you can get fiber, you can get nano powder, you can get ceramic materials by various techniques. First, you get a solution, you can wait for gelation time, and you can dry, supercritical drying and sintering will give ceramic. You can just dry this gel to get powder, nano powder, or you can directly use this solution to get thin film, fibers or powders. So using this sol gel method, you can prepare different kind of nano materials. So the steps that are involved in sol gel method are following. The desired colloidal particles are dispersed in a liquid to form a solution. First, we are going to form a solution, and then the solution is deposited on a substrate by spraying, dipping or spinning. Once we deposit the solution on a substrate, we are going to wait for some gelation time, during which we get a gel. Okay, so then final heat treatments of this gel, we will get the desired nanoparticles in the crystalline or amorphous state. What are the benefits of this sol gel method? The benefits of the sol gel method are high purity and uniform nanostructures can be formed using the sol gel method. And normally this sol gel method is used to prepare metal oxide nanomaterials. So this is the sketch, and so we have basically discussed the sol gel synthesis using a neat sketch. Explain how the electrical and mechanical properties of nanomaterials vary with size. So electrical and mechanical properties. Here I have discussed various properties of nanomaterials which change as we go down in size. Okay. For example, physical properties decrease in melting point with size. As you go down in size of these nanomaterials, the physical properties changes. What physical properties changes? Melting point will decrease. Similarly, chemical properties will also change. When you go down in size, better catalytic efficiency through higher surface to volume ratio. So when you reduce the size of these nanomaterials, the materials which are not catalytic will become catalytic. Similarly, electrical properties change. The materials which are not electrically conductors, they will become conductors as you go down in size. Magnetic properties change. Coercivity and they will exhibit superparamagnetic behavior as we go down in size. Mechanical properties change. Improved hardness and toughness of metals and alloys, ductility and superplasticity of ceramic material. So when we go from bulk to nano size, so various properties change. Physical properties, chemical, electrical, magnetic and mechanical properties, optical properties and biological properties. So basically we need to discuss only mechanical, electrical properties. So electrical properties we have discussed. Materials which are insulator, for example, will become conductors as you go down in size. Materials which are materials will improve their hardness and toughness as well as ductility and superplasticity as we go down in size. Okay. Explain how the chemical and optical properties of nanomaterials vary with size. Similarly, so optical and chemical. So we discussed just now. So materials which are not catalytic in bulk size will become catalytic when you go to nano size. And optical, when you go from bulk to nano, spectral shifts of optical absorption and fluorescence increase quantum efficiency of semiconductor materials. So they will exhibit fluorescence and the quantum efficiency of semiconductor crystals when you go from bulk to nano size. Differentiate chemical vapor deposition and physical vapor deposition techniques for synthesizing the nanomaterials by drawing their sketches neatly. So what is first vapor deposition technique? A vapor deposition refers to any process in which materials in a vapor state are condensed through condensation, chemical reaction or conversion to form a solid material. So that is the meaning of vapor deposition technique. So these processes are basically used to form coatings to alter mechanical, electrical, thermal, optical and corrosion resistance and wear properties of substrates. That is why we use vapor deposition technique. Basically there are two different types of vapor deposition techniques, chemical and physical vapor deposition techniques. So physical vapor deposition technique, in this method there are different steps. So first is that we need to we need to prepare a method for depositing the metal. Then combination with an active gas. Once we prepare this metal, then we need to combine this with an active gases such as nitrogen, oxygen, or methane, and then we are going to use plasma bombardment to coat this metal onto a substrate that should have uniform coating. That is why we are using plasma bombardment. So there are different methods in physical vapor deposition technique: iron plating, ion implantation, sputtering, and laser surface alloy. Okay, so this is the schematic of physical vapor deposition technique. So thermal evaporation is one of the simplest and most popular synthesis techniques in physical vapor deposition, and it has been used very successful and versatile in fabricating nanobelts and nanowires. So this is one of the technique, and this technique is used to prepare multi-wall and single-wall carbon nanotubes, and metal catalysts such as gold, tin are also prepared using this thermal evaporation techniques. Chemical evaporation technique is widely used for depositing thin films for a large variety of materials. So chemical vapor deposition technique is used to depositing thin films. Okay, so applications are in fabrication of microelectronic devices and protective coatings. So in chemical vapor deposition technique, reactant gases at room temperature enter the reaction chamber first, and the gas mixture is heated as it approaches the deposition surface, and then depending on the process and operating condition, the reactant gases may undergo homogeneous chemical reactions, and so then this will be deposited on the substrate. Okay, so these chemical vapor deposition techniques are used to nanomaterials of metallic oxides or metallic carbides can be prepared by these techniques, where we use metal and oxygen or metal or carbon in a vacuum chamber to gaseous phase. We heat this metal and oxygen or metal and carbon. So we heat them, and once we get them in a gaseous phase, and then we are going to deposit these gaseous particles onto a substrate. That is how we've prepare these metallic oxides and metallic carbides. So there are variety of chemical vapor deposition techniques. For example, given here: atmospheric pressure chemical vapor deposition, plasma assisted chemical vapor deposition, low pressure chemical vapor deposition, photochemical vapor deposition, chemical beam epitaxy, and chemical vapor infiltration. And this is the schematic of chemical vapor deposition technique. Explain the following: nanoscale, nanoscience, nanotechnology, surface area to volume ratio, and quantum confinement effect. So nanoscale, the word nano is derived from a Greek word meaning dwarf or extremely small. So the meaning of nano is extremely small. Okay, and it is 1 billionth of a unit. Okay, 1 by 10 power 9 is 1 nanometer. Okay. So a nanometer is 1000 millionth of a meter. Okay. So 1 nanometer is 10 power minus 9 meters, or 10 power minus 6 millimeters, or 10 angstroms. So 1 nanometer spans 3 to 5 atoms lined up in a row. To understand what do you mean by nanometer, if you can think of one atom, 3 atoms you can put in 1 nanometer size. For comparison, a single human hair is about 80,000 nanometers wide, and a red blood cell is approximately 7,000 nanometers wide. Scientists and engineers are nowadays interested in the nanoscale, which may be taken as 100 nanometers to 0. nanometers approximately. Below this lies the atomic scale, which is around 0.1 nanometers. Therefore, nano world is a borderland between quantum world and macro world. So you have a macro world which is centimeters, millimeters. You have a quantum world which is angstroms and below, and this is in between. You have this nano world. Okay, macro world, quantum world. In between these, you have nano world. So just now we have discussed what is nanoscience and nanotechnology. Yeah. So, and we also discussed surface to volume ratio and how it increases when you go down in size of the particles. And we also discussed quantum confinement, how the energy level changes when you when you have this quantum confinement effect. and how the properties change when you have this quantum confinement effect. For example, opaque substances become transparent, inert materials become catalysts, stable materials become combustible, solid turns into liquid, insulators become conductors. Discuss in detail how the mechanical magnetic properties of nanomaterials vary with particle size. Mechanical and magnetic properties. So mechanical properties, when we go from bulk to nano, the toughness of the metals and alloys will be improved, and ductility will also be improved, superplasticity of this ceramic material. And magnetic material, increased magnetic coercivity up to a critical grain size, and paramagnetic behavior when you go from bulk to nano size. Mention any three properties of nanomaterials and how they vary with size in detail. So again, there are many properties given here. When we go from bulk to nano size, the material properties change. So physical properties change. For example, melting point will decrease when you go from bulk to nano. Materials which are not catalytic will become catalytic materials, catalytic behavior when you go from bulk to nano. Similarly, which are insulator will become conductors, and which are so they will magnetic properties, they will exhibit superparamagnetic behavior, and they will mechanical properties, improved hardness and toughness, and improved ductility when you go from bulk to nano. Optical properties, they will exhibit fluorescence, for example, and biological properties. They increase permeability through biological barriers, for example, blood-brain barrier and membranes. So these are many properties that change when we go from bulk to nano size. Okay, so that is what we have discussed. So these are some of the textbooks I used in this presentation and references to look at if for clarifying any doubts. And to summarize, I have discussed 10 theoretical questions and what are the answers to 10 different theoretical questions on nanotechnology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.